Alrighty, folks, we are going to jump into module number 25, and this is week 7, the final week of the course, where we're going to start wrapping things up. And we've got some fun topics for this week. So we're going to start with some advanced topics, and this week really is all about just advancing your C++ and helping you get excited about C++ for your future. So you'll notice that there's no more assignments here. We're going to have two sort of advanced topics days talking about things that push C++ projects a bit further. And then as well as maybe another flex day where I might have another topic at my discretion, while these other ones were ones that folks were interested in, and then we'll just wrap up the course and have a finale live session, and that is it, if you can believe it. Summer 1 moves so fast. All right, so let's go ahead and dive into our topic today, which we're going to be talking about Python in C++. So kind of a fun topic here, and maybe not the topic you were expecting. So I think this will be a nice one to, again, motivate C++, your future learning, and combining it with another language that you might also have some interest or experience in. Okay, so again, the final week, just a reminder on the schedule here, just to pay extra attention on our warm-up, that A9 doing the image processing in parallel is due June 25th. And then, of course, today the spline assignment is out. Okay, so lots of folks have been working hard on that, which has been nice, and hopefully those were fun ones to put together and refactor a little bit, and we wrap up this course. Okay, so last time we discussed move semantics. So this idea of using std move, and this is another type of constructor that we can write in a sense, that it's another way to talk about how do we construct or create a new object. Well, in this case, we can construct a new object by moving over the data from an object that has been previously created, and we think of this as transferring ownership, thus avoiding the need to make a copy of an object. So we're literally moving the contents of one object into another. So in this case, it might be a pointer that you're reassigning, and so on. But the idea is you're moving the data over, and that's, in a sense, destroying or rather just, again, transferring the ownership to that object. We looked at an example to show how that can be useful in the sense of avoiding copies. Because if you have lots of copies that you're making in your program, that's lots of information moving around, and that's expensive to otherwise manage and can hurt performance. Okay, so that was last time. Again, just a reminder on course logistics. This is the final week of this course. Again, I can never believe it for how fast the courses move. So we're not going to have any more new assignments this week, as you know, there's only so much we can add to the course in a sense of these fast summer semesters. And I want to give folks a chance to wrap up their image processing and spline assignments and finish strong. Otherwise, do make sure to complete the in-class activities. For the most part, these are going to be relatively simple this week to, you know, maybe one question, one answer. I just want to make sure that people are completing them and watching the contents, the videos. And again, these week's lectures are just designed to keep you excited about learning C++ for your future, because there's so much more to learn. And this course is what I've hoped been a helpful introduction to the topic. You know, maybe we don't have mastery yet, but we at least have experience. We know some of the important things, and we've worked in the language a little bit, which is the goal of this course. So when you see it again or have to use it at a co-op internship or so on, you have some experience doing so. Okay. And the last announcement, which I'll make you know, probably every lecture this week, to be honest, and Piazza, is just to fill out your trace. And again, I'll just make sure that there's reminders out. That helps me out as an instructor. I do read every response, and I use the feedback to improve upon the course, this specific course. And then if there's any general feedback, I also apply those to all of my courses. You'll notice my websites, for instance, always get updated. Sometimes that's feedback from students, but it's just a way that I like to always improve. And it's likely that I'll have a lot of you, you know, perhaps in a future class. So that benefits you directly. To provide that feedback, and I do take it very seriously and enjoy reading those, you know, as soon as they're available. So just a reminder to do your trace. All right, so with that out of the way, let's go ahead and talk about our topic for today: scripting languages, and a little bit of a programming language refresher here. Just compiled versus interpreted languages. So of course we've been talking about C++ in this class, and the idea that it's a compiled language. That means we're converting text into machine code. that means the ones and zeros. So that's this first sort of process here where we take some source code here, a C or say C++ would be an example of a compiled language, translate into machine code, and then our computers run that code. Now, other languages like Python, which many of you have used, I know folks in the data science program who have taken DS 2000 or 3000 have used Python. But if you've used JavaScript or any other of these scripting languages, you just have this interpreter stage that reads your lines of codes, interprets them, and then just gives you the result directly. So there's not this compilation stage here, okay? It's just immediately reading the source code and based off of the instruction given, executing the code here, okay? So compiled languages usually benefit from going through this compilation stage to machine code because you don't have to reinterpret the results over and over and over again. And that can often result in a very big speed benefit for that particular language. Okay, so this does come off a trade-off though, in the sense that when you compile the code though, you do have to recompile the code every time you make a change, right? And we've learned that process here in C++ in the sense that, right, I've always been telling you to save often, recompile. You've seen me do that in Vim many times where I'm constantly writing to the file and recompiling it, and that does take some time. And that's the advantage of an interpreted language, or in other words, a scripting language, because you just have to save your file and then you can run it right away. There's no compilation stage. You don't have to wait at all. So the code itself might execute much slower, sometimes 10 or even 100 times slower, but there is more flexibility often within the language and also just in your ability to iterate as you're developing the code. Okay, so just to give you some sort of execution times, roughly speaking, these are from some benchmarks. So you'd have to look at the actual code that's being run, but languages like C++, which are compiled versus, Python, there's roughly 100 times faster speed performance, which, if you're writing a game or, some of the graphical applications that we've written, for folks who went through the Falling Sands project, for instance, that can really improve, the application's usability if it's actually 100 times faster. But for maybe small applications it might not matter, like if you're loading a web page, for example. PHP is a web scripting language, and it doesn't really matter if it's executing 100 times as slow if it only needs to load once and you're just looking at very simple content like text and images. Okay, so that there are some trade-offs here that we have to understand with each tool, but by default, one of the reasons we've been learning C++ is because of its performance and ability to control performance. Even the stuff we learned like last time, like the std move, move semantics, having those features available to move data around faster, it's really what C++ is all about. Okay, so again, why interpret code and sacrifice speed though if I'm saying, C++ is so great and it's so fast? Well, again, these trade-offs is that when you start working on projects at scale, it can take several minutes or even hours to compile projects. If you imagine trying to fix tiny bugs, for instance, just for small changes and having to wait an hour to see that particular change, that can be very frustrating, right? And time is money in the software industry. So, plus it's just not that fun to constantly be waiting for you to have to recompile your code. All right, so one advantage is that if you can interpret your code, though, is if you can sort of separate out tasks that need to be iterated on quickly and do those in a scripting language, right? If you're just processing some data, or maybe if you have a graphical user interface and you're able to script part of that in a scripting language, that makes your application sort of more data-driven in the sense that you're just writing, say, Python or whatever scripting language scripts that don't need to constantly be compiled. The other reason that we're going to want to learn how to interpret code, though, is that we can extend our applications, our C++ applications, by embedding an interpreted language like Python into C++, okay? And then you can have part of your code base be implemented in C++ and the other part implemented in Python, which is pretty cool. Okay, so I want to just give an example of one of the benefits of rapidly developing applications. So this will be something for you folks to try to watch here. So anyway, here's a YouTube video for that. I'm going to go ahead and just mute it here. And he talks about how to sort of iterate and design a little bit. And there's this pretty cool application here. And I'll go ahead and make the quality as high as possible. I know it's a little bit hard to read here. But basically what he's got here is an application here on the left. And he's using JavaScript to just iterate and change various parameters. And you can see the changes right away. So you can imagine as a designer building this application and being able to see this sort of live coding, which is what this technique's called. This makes it very helpful, right? You just click on an integer value and use a slider to sort of move things around and get the value right. This is pretty cool here. So anyway, this is a little talk to inspire you about the benefits of scripting languages, and then we'll get into how to combine this with C++ here. Okay, and this is a very nice talk if you're just interested on more of the, say, design side of things. This will sort of show how to combine some of the technical stuff that we've been learning with C++. It's very technical, scripting languages, and then ultimately design interesting applications here. Okay. But anyway, this is showing a clear advantage of scripting languages because you can see the changes right away without having to recompile the code, save, and wait. You can just very quickly iterate. And an artist probably cares much more about getting this scene to look correct as opposed to how fast this code is working. Okay, so in order to optimize our development time, we really have two options here. And what I mean by this optimizing our development time, that means taking a scripting language and putting it into C++. Okay, so scripting language can be actually embedded within a compiled language. That means our compiled language, C++, where we're doing all these sort of heavyweight, complex math operations, setting up different systems, and so on, can still be done in C++, but the actual logic of our application can be iterated on in a scripting language. Okay, and then our C++ application is actually going to load the script at runtime when the program's just about to run. So it'll open a file that's a script and execute it, okay, one line after the other. And that's pretty cool. So then you don't have to recompile your C++ code unless there's major infrastructure changes. Otherwise, you just make changes to the Python script, for instance. Okay, so here's what I mean by embedding Python into C++. Okay, so here's an example of what you can actually do. So Python has a library here. You can see the .h file here. And this is your C++ code, but you'll see this block here where there's different function calls to the Python application programming interface that allow you to initialize the Python interpreter within your C++ program here. So you can see within this Python here, you're executing a simple script here using Python from your C++ application to import the time library and then print time. And this is doing this all in Python here, okay? And then C++ and Python language are able to communicate through this API, and thus you can use the scripting language to do things that you want to do in Python, and then use that information or capture that information or the output in your C++ application and so on. Okay, so this is a really cool idea here, and we're going to actually see it in practice in a few moments. So the other option that you can use too to sort of optimize your development time is to use a scripting language like Python, but build your application as a library in C++. Okay, so what do I mean by this? Well, this means that you do something in C++, like you build a math library, a graphics library, some data science library, some really heavyweight tool in C++, and then you compile it into a library. Okay, so we've used various libraries like SFML, for example, but that's an example of where we compile our C++ code as a library, and then we're going to link it in, except we're linking it into a scripting language like Python. So then our Python's using this library here. If you're on Windows, it's usually .dll. If you're on Linux, it's a .so file. If you're on Mac, it's the thing that ends with .dylib. These types of extensions. So you compile your program here, and then from within Python, you import whatever your library is. Okay, and then your scripting language Python is actually executing the C++ code. Okay, so any of the Python libraries that you're using, for example, so if I just launch a Python interpreter here, if I import the random library here, and I have to remember how to use it. Let's see, help random here. Basically, somebody implemented this in C++. Okay. So if I use random dot, let's see. Let's see, and here's a bunch of, so I just hit tab here. Here's a bunch of functions that are written, but these are all probably loaded from a C++ library so that I can randomly generate some number here. Okay, random, I can do something like 10 or something like this. Or I can just call the random function here. So let me just clear the screen here. Random dot, got the parentheses, there we go. So this will just generate a random number between 0 and 1. But this has been implemented, this function in a C++ library. And when I did this import random, that loaded this library, this C++ code, into Python. Okay, so just an example of what's going on there. Okay. Okay, so again, here's what I mean by using our application as a library within Python. So we want to wrap our C++ code to be used from Python. So it would look something like this, where we write our C++ code and then we use the Python library to create a Py object. That would be sort of the return type. And then we sort of set up the C++ object in this way. Okay. Now this looks a little bit messy, so what I'm going to provide today is just a little teaser of sort of our advanced topic is how we would actually do this, okay? So I'm going to move on a little bit here because we're not going to be using this style of syntax because this looks pretty nasty. If you've done some Python, this sort of makes sense. You sort of see the self thing, that there's this idea there's arguments here. But these objects are a little bit messy, so I'm going to introduce a library at the end of today and show you an example of how to actually do this. Okay, so again, how's it done? Well, first, a scripting language has to be chosen that we want to be able to use. In this class, I'm going to talk about Python, but some other popular ones are Lua, Ruby, JavaScript, or you can even write your own language, your own scripting language. So some of you are going to go on to take compilers courses here at Northeastern. That's one of the things we're known for, programming languages and compilers. And then you'll have enough knowledge to actually build your own programming language, which is pretty cool. Okay. So I'd say, the two most popular, again, are Lua and Python. Lua is used in World of Warcraft, various game engines. They're all sort of Lua based. So you write the code in Lua, but they're really just calling into C++ libraries to do the heavyweight lifting. Okay, a big game like this, for instance, needs to be written in C++ in order for you to get good performance. Okay, Python, on the other hand, again, very popular general purpose scripting language. It's also used in various game engines, game frameworks, 3D tools like Maya, 3D Blender, 3D. Maybe some folks on more of the design or art side have seen some of these. But you'll see the actual application here, which is all drawing the graphics and so on in C++. But in this little window here, you'll actually see that there is Python code being written for the actual logic. Okay, so the heavy lifting's done in C++, but the lightweight stuff's done in Python to just organize its sort of logic or how something must take place. Okay, so there are some trade-offs between various scripting languages, even like Lua and Python, but I won't get too much into these because I've already by default I'm just going to show you Python in this class just to again get you excited about how to combine C++ with some other languages. But at the end of the day, Python's pretty easy to work with, and there's this nice framework called PyBind 11, which lets us use modern C++ 11 and beyond features that makes this fairly accessible for us to investigate. Okay, and as I mentioned, Lua is another popular one. It's only a single header file, which makes it sort of nice to just include. But you could build your own scripting language as well. Nothing stops you from doing that. So AngelScript's a nice example of this if you want to take a look at this. And I'll provide some resources in this class at the end if you're really into this idea of building your own language. I think that's a really cool thing and something, it's a great learning exercise as well. Okay, so what I'm going to use is PyBind 11 though, so let's go ahead and dive into it. The best resource is, of course, reading the documentation here. So I think this is a pretty good guide here, but I still want to walk you through a little bit of this setup. In fact, I've done some of this setup mostly today. I just want to show you what's possible so you know what's possible. And then if you want to do it, I'm going to reference you to some, or refer you rather to some YouTube videos to show the setup on Mac, Windows, or Linux operating systems, okay? Okay, so what is PyBind? It's a tool that wraps your C++ code into a library of code that Python can understand. Okay, so you build your class in C++, okay, so some type of object that you want, and then PyBind 11 wraps it and uses that class in Python. Okay, so it's going to handle the fancy things like making C++ work with Python, the different data types, for example. And it's all wrapped up in this library. Again, which is pretty powerful stuff. It's pretty cool. So the general walkthrough here, and I'm going to do some of this, or at least show you how to use it, is to download PyBind 11 from that previous link here. Download Python, and we're going to use version 3 and beyond. Again, for those folks on the data science track, maybe you've done Python 3 or beyond, or maybe just other folks have also investigated this. And then we need to download the PyBind 11 module here. Okay, so from Python, you can install it using pip3 install Python 11. Okay, so here's the big idea for doing this is you include the PyBind 11 header, something like this. You write a C and C++ function, something like this, add, so just like we've learned here, and then you bind the function or wrap it using PyBind 11. So you wrap it here, you'll see it all in caps here, whatever the module name is, any documentation you want, and then the function that you want to wrap here. And you'll see how do you want to name that function, add, which matches here, the address of that function, ampersand add, and then a little comment here describing that function. Okay, so that's the idea. Now the rest is about how do you create a shared library, and here's the example for Python 3, and this is something that I've recorded a few videos on. If you do want to follow along and actually try this, if this is inspiring for you, then this is the compilation, and this is building a shared library here for that example project, so that when you're within Python, you can import this example module and then do example.add, and it's calling your C++ library and performing the add here in Python, which is pretty cool. I think this is a really cool idea. Okay, and now we're not just limited to functions, however, when we do this, we can actually wrap data structures that we create in C++ as well. So again, if you've ever wondered in Python, where do these modules come from? Well, they're coming from C++ most of the time, because that's where we get our performance from. So someone's written their own structure, and this example from the documentation, it's just a pet here, and they've written some member functions here, like setting the name or getting the name and so on, maybe some member variables, and then they wrap them with PyBind 11 here. We have this class here. What the class is, pet, what module it's part of, and what we're going to name it, and then the different member functions that we want to expose in our library here. Okay, so in a way, this is sort of exporting out as a library these particular functions. Okay, so again, what's cool about this is we get the high performance of our C++ compiled code in Python. Okay. If we also design things properly in C++, like when we allocate and delete memory, in our C++ classes, again, taking advantage of that RAII, the resource acquisition is initialization principle, where when we create an object, that's the only place we allocate. When we destroy the object, that's the only place we destroy memory. We don't have to worry about memory allocation or anything in Python. Okay, we just simply take advantage of that fact that makes things really simple to use in Python. Okay. Then we get all of Python's data structures. If you're used to programming in Python, maybe you missed that in this class, but you get the list data structure, dictionaries, and so on. Okay. Now, some difficulties you might face, or where this is sort of confusing, is this idea of building a shared library. That might be a new idea. That's not something we've covered really in depth in this class. We've talked about using libraries, but this idea that you can actually compile your code into a library and share it with someone, this is how it's done here. And the main important things here are this -shared flag that says, hey, I'm compiling my program, but I want it to be a shared library. The standard we're using, so 11 and beyond. And then this flag here, -fpic, means we're generating position-independent code. That means the code that we're compiling can be linked into other projects and sort of glued into other projects without causing too much difficulty. Okay, so this is just part of the compilation flag. It basically means the code that we compile can be easily moved around. So build it in that way on the compiler's end. Okay, and then the rest of this is between the little quote here is from Python. This sets up all of our includes. So we're including all of our header files from PyBind 11 here. Okay, the C++ file that we want to compile, and then what we're going to output this library name as example. Okay, and then any other additional libraries that we need to include. Okay. And of course, the other difficulty you might be running into watching this lecture is just saying, hey, I don't know Python. I haven't taken DS2000 or some other course where we use Python. Well, the good news is Python you can pretty quickly get started with. It's much simpler than C++. You just type in commands as you learn them into the interpreter, and it sort of generates the result. The scripting languages are much easier to get started in. Okay, so at this point, I'm going to give a little break, and then I'm just going to show you an example of our first advanced topic here, and something to get excited about or to be thinking about if you want to start building your own libraries and making them accessible from within Python. Okay, and if you give yourself a little bit of a break, let's go ahead and just walk through a first example of using PyBind 11. All right, so there's two sort of ways to get set up with this. The first is that I have set up a playlist here, video. So if you're on Ubuntu, Windows, or Mac, you should be able to get set up with one of these operating systems to follow along with this example if you'd like. And again, today's just sort of for fun or the advanced topics, although I'd recommend trying because it's a good experience to understand how to compile a shared library. So most folks are going to be here if you're using the virtual machine and can follow along with these directions here. So I'm going to go ahead and as soon as this commercial gets out of the way, show us this example. So this example is just going to be following along from the PyBind 11 tutorial. So let me go ahead and just open that up here and show you how to get started. So the first steps are again covered in the video for how to sort of get started on your respective operating system. So what I'm going to want to do is just figure out, how can I expose some really simple function like this add function to us in C++. Okay, so let's go ahead and do that. So I'll go ahead and open up a terminal. And I'm going to open up into our CPP directory, our module 25 directory, and move into that here. And let me go ahead and just split the window to make it a little bit bigger. And let's follow along here. Okay, so what do we need here? So let's just go ahead and create this. I'm just going to call it example CPP. Okay, and for our libraries, when we compile them, we can just have the function that we want here. Okay, so I'm just following along with what we've got in the tutorial here. I don't want to do anything super complicated right now, but let's just start with that. Okay, so now I always have the option to just compile this code here. Okay, and let's use C++ 17, compile, and our function called example. And let's see, little compilation error here. So I can always just compile the object file. Remember that we've been able to do that. In a sense, this is our library that we could link into other projects if we want here, okay? But what we're going to want to do is actually just compile this into some library file. So not a .o file, but it's going to be a .so file in Linux, okay? So let's set up the rest of the PyBind here. Okay, so first things first, let me go ahead and include the PyBind module. So PyBind 11, PyBind 11.h. And let me just see as far as if I try to compile this, will this work here? Okay, so it's going to complain here that it doesn't know where python.h is. And the reason is we haven't told it in our compilation where that include file path is, okay? So you can either follow along in this video by using the provided compilation steps here, or rather in this tutorial, or you can go to whatever the respective operating system you're using, Ubuntu, Windows, or Mac, and look in the description here for the compilation line here. So again, we're compiling this as a shared library, and we need to tell it where to find our includes here, okay? So let's go ahead and add our includes here. And I'm just going to copy this here and see if this gets us any further here. And I also want to use, because we're compiling as a shared library, I'm also going to add these compilation lines here. So shared library, this flag for position independent code, and then we have our standard here. The code I am compiling here is our C++ file, our includes, and then at the end I'll put our output as, let's just call it mymodule.so, so following along with what we have here, okay? So let's try this much here, and it looks like it's pretty happy so far with this, okay? Now, something that might be new with how we're compiling here is occasionally you're going to see this in bigger pieces of C++ code, and that's one of the reasons why we're doing this advanced video, is, what is going on exactly here with this tick mark? How is that able to be part of this compilation here, okay? So let me go ahead and just rotate it just to make it a little bit bigger, just so you can see what's going on here. So this compile is fine. So if I actually echo Python 3.6-m pybind 11-includes, let's see if this gives us anything here. And it actually will. So what this is doing here, this line here, whenever I put between these tick marks, which are probably by your one key, the sort of backwards looking quotation marks that are slanted, it's actually interpreting, okay, from Python, the module here, and then if I pass these flags includes, it's actually setting these include flags to say, hey, where do I find all my Python 3.6 flags here? So you can see that it actually generates these extra include paths. We could otherwise just paste these in instead of executing this. So you'll see this, what I've highlighted here, occasionally in C++ projects, meaning that it's calling Python 3.6 and telling it to do the work of where these include paths are, okay? So this was something that took me a long time to understand, so I want to at least show you what's going on here. So if you ever run into this on an advanced project, you'll understand what's going on here, okay? Now we are missing a few other flags here, but it looked like it made our module here, okay? But let's go ahead and, we haven't done anything with PyBind yet here. So let's keep following along in our basic tutorial here to actually wrap this function here so that we can use it inside of Python. Okay, so I'm going to switch back up here, and I'm going to do PyBind 11 module. I'm just calling this example M here, and let's see if we can get this wrapped up properly. So we can add a little bit of documentation, which is sort of a Python thing here. So part of the module, the doc string in Python, let's just call it 3520 example. Okay. And then let's add, well, what do we want to add to this module? Well, our add function here. So I would just do m.define. So it's part of this module here. And PyBind inside of this library is taking care of, from within this function call, it has its own sort of global, or perhaps it's a singleton object, if you learned about this pattern, way to add different functions here to the module that we are creating, okay? So the name of it, so just some string, and then the address of this function here, okay? And then any comment, function that adds to ints, okay? And then we just end it there, okay? Now let's try to compile this again with what we have here. Appears to work. So let's go ahead and try to see if we can import my module into Python. Okay, so if I do Python 3 to launch the interpreter, then I import my module. Let's see. Doesn't seem to like that. So what was it? Example? No, it wasn't either. It was my module. So we need to do a little bit more work still on our compilation to fix this. So recall here that we want to also link in some other flags here for our linking in of our PyBind 11 library. So let's go ahead and do that here. So I'm going to go ahead and use the same trick where I use Python 3.6, and there's a tool called config here. And LD flags will load in all of the Python 3.6 libraries for us, okay? So let me just echo out what that means here. Python 3.6, config, LD flags, and you can see all these libraries that need to be linked in. For example, we've looked at pthread, for example, which is needed in Python. Some of these other libraries here. M is just short for the math library, and so on. Okay, so this will help us generate a correct module for us, okay? So that's been created. I'll just go ahead and create it one more time. Now let's try Python 3.6, which I have running. Now let's try importing my module here. Let me just be a little bit careful and a little bit more consistent with how I am defining this here. Oops, let me go ahead and quit out of here. And I'm just going to call this example.so, just so that it matches what I have here in my file. And let's see what happens here. And if I run Python 3 and then just import example, now it's happy. So it needs to match this name here of the Python module that we're exporting. Otherwise, it'll get a little bit confused. So there can be some little tricks like this that you have to be a little bit careful with. But it's kind of cool that it'll work here. So now if I do help and then I wrap example, it'll tell me that, hey, I have this add function as part of my example library from our 3520 example library. And what does it do? Well, it's this function that adds to ints, so that comes from here. Okay, so now if I try to use this, it's not just the add function, but remember it's going from example add and then 5 and 2, for example. And I get 7. So this is executing C++ code within the Python 3.69 on my machine interpreter. And I think this is really, really powerful. And again, you could write some other functions here. So if you want to play around with this, you now have that ability. So let's just do, a multiply instruction here to just sort of change this. And then we want to also export that multiply function here, mult, the actual function that multiplies two integers, okay? So I need to recompile the library. So I do need to do this recompilation step, but ideally I'm not doing that as often as I would a normal C++ code base, okay? So I've got the module here. Let me go ahead and remove my module here. And then we just do Python 3. I can check out the library here once I import it, example, and then do help, example, and I can see we now have that multiply function here. So again, what's cool is I can create, a list of, something, and I can use it with these add functions here. Okay, so add 3 and 7, multiply 1 by or 2 by 9, and let's go ahead and see what happens. Oops, so it doesn't like add because it has to be example.add. So there's ways in Python that you can import as and so on here. So now it'll be happy here. So now if I just print out the list, you can see that I'm using my C++ functions here to create a Python list of whatever these numbers mean if they had some sort of value. But I'm able to sort of combine the two languages. So if I really like some of the code that you've written, perhaps in one of your assignments or one of the classes, like say the spline assignment, you could export out that spline as a module and then wrap it up and use it in Python 3. Okay, so that's the idea. This is creating a library. You can do this for classes as well. I like showing it for functions. It's nice to just think about it for functions now. But there are some other examples here about how to wrap up objects here. Okay, so let me just open this up a little bit. So if you want to do object-oriented code, there's an example of wrapping a class here as well. Okay, so that's sort of the standard example, and that's another one of the examples that I go through in the video. So this is pretty cool, and it's as simple as just doing this. You just wrap the class in your module like we did and define each of the functions. Okay, so let's go ahead and start wrapping things up here. That's about where I want to go. All right, so that's been our PyBind example, and I've just added the samples here. So what's really cool is there's some nice books too. If this topic is really interesting on scripting, of course I want you to check out the PyBind stuff, but there are some other good books that may be of interest on writing compilers and interpreters or game scripting mastery. Both are a little bit older books, but they're still really good. This information doesn't really change, and these are good sort of well laid out books to use for your journey into scripting, if you especially want to think about embedding scripting languages or developing libraries of code. I'll say, for embedding scripting languages, this is something very commonly done in games and graphics applications. So you can see that's why I've chosen some of those applications. But the idea of building libraries that are called in other languages, that's ubiquitous in pretty much everything, especially for folks with the data science focus taking this class. When you go off to use libraries like PyTorch or these sort of things, they're compiled in C++, and that's what you're actually using. So just so you understand what you're using, okay? So again, I didn't show an example of embedding Python within C++ here, but there are some on this playlist if you want to see embedding the interpreter. There's about an 8 or 9 minute video on how to actually do that. In fact, I'll just sort of fast forward to the piece here after we get through these commercials. So you can actually see how to execute Python from within your C++ code. So I'll show you how to compile it, errors and things that you might run into, but it's a pretty cool idea that you can do it and do it so simply using the PyBind infrastructure. Okay, so that's it for this video, folks. I hope this one was interesting as far as an advanced topic of just something maybe you didn't know you could do or were wondering how it's done in C++, and we'll continue going further from there. So there's one short class activity from there, and then we'll pick it up tomorrow for our next activity. All right, take care, folks, and we'll see some of you in office hours this week as always. Bye.